This is Stat 101, Examples Class 11, Example 3, a chi-square test for two-way table data. So this example, we have data on 150 chickens divided into two groups according to breed and into three groups according to yield of eggs. So this is two different breeds, Rhode Island Red and the Leghorn chickens, and the yield in some sense, which is high, medium or low in some determined way. So again, this is categorical qualitative data. The chicken is either Rhode Island Red or Leghorn. The yield is either high, medium or low by some categorical value. So what we're looking at here is, are the data consistent with the hypothesis that yield is not affected by the type of breed? So what we're looking at here is there any evidence to suggest a difference between those? We're testing at alpha equals 0.05, and how are we going to do that then? So first thing that we need to consider is the hypotheses. Now, for a chi-square test of independence, the null hypothesis is always that the variables are independent. And if they're independent, it means there's no association or no relationship between them. The alternate hypothesis then will be that the variables are not independent, which means that there is a relationship between them. So for our example here, we're looking at whether egg yield and type of breed are independent. That would be the null hypothesis. And the alternate hypothesis would be that egg yield and type of breed are dependent, which would tell us there was a relationship between type of breed and egg yield. So, in order to do the problem, we're going to go into Excel and work out those observed and expected values for the chi-square statistic. But before we do that, we'll transfer that idea of hypotheses into our template for the hypothesis test. So the null hypothesis is that egg yield and breed are independent, and the alternate hypothesis that yield and breed are dependent. Now remember that we were working here with alpha equals 0.05, and the calculated value for degrees of freedom for a chi-square test, number of rows minus 1, multiplied by number of columns minus 1, and we have data where we have two rows, that would be the two types of chickens, 2 minus 1, and 3 columns for the different yields, 3 minus 1. So 2 minus 1 multiplied by 3 minus 1, that's 1 multiplied by 2, which is 2 degrees of freedom. And so we'll go into Excel now to work out the chi-square statistic. So in here we have the observed values from our table, high, medium, low yield, and different kinds of chickens. So recall that to find the expected values, we need formulas of the type row total multiplied by column total divided by overall total. So here we've got the observed values, we've taken those totals and replicated them in an expected value sense. So for medium, we have row total multiplied by column total divided by overall total. And notice when we've done those two calculations, the third of those figures would be fixed because the total must be 103. But we'll do the calculation by row total multiplied by column total divided by overall total, and that way we know that our calculations are all done by the same method. So again, high yield and Leghorn, that would be row total multiplied by column total divided by overall total using the cell references, row total multiplied by column total divided by overall total, and of course we could do column total multiplied by row total divided by overall total. We've lost our figure. 47. Divided by overall total. And this gives us the expected values in a spreadsheet, which means that Excel does all the work for us and keeps the calculated values in a form so that they are accurately taken through the calculations. So in order to find our chi-square statistic, we need to replicate those expected values, which means that we can take those cell references and transfer them into the expected column. Make sure that as you do this, those expected values fit with exactly the same positions as in the observed totals. So the columns, as we go down this column, we're taking the numbers from each of the individual rows and columns, and we're just taking the cell reference across into a calculation for the expected values. So we have a column of expected values, which each of those expected values corresponds to the observed value in the table above it. Now, for the chi-square statistic, we need to find the difference between the observed and expected values. So using cell references again, we take the observed minus the corresponding expected, and if we take that figure, we can then copy it down the row of the column, and we get each individual value. Now, the next thing is to square these individual values, because we're trying to make up observed minus expected squared divided by expected. So do the squaring first. And again, copying that down the column will do each individual calculation for us. And now we're dividing that observed minus expected squared by the corresponding expected value. And finally, copying that down the column will give us each individual value that makes up the chi-square statistic. The chi-square statistic is found by taking the sum of all of those, and so the sum of the observed minus expected squared divided by expected will give us the chi-square statistic. And of course, to do our hypothesis test now, we need to find the critical value of chi-square, and we can get that with CHI-INV. And if we use CHI-INV, it will ask us for a probability, and the probability that we had here was 0.05. We were testing at the 0.05 alpha value, and the degrees of freedom we had was 2. Row total minus 1, number in the row minus 1, multiplied by number in the column minus 1. And that gives us a critical chi-square value of 5.99. So for this example, we're doing our evidence by comparing the chi-square statistic with the critical chi-square value at alpha equals 0.05 with 2 degrees of freedom. Now we'll take those figures back into our template and recall that the chi-square statistic we just calculated was 4.07, and that came from a formula which we used in Excel, which is that the chi-square statistic is the sum of observed minus expected squared all over expected. And we calculated those values step by step and added them all up at the bottom of the column. So we found those values from Excel. Also in Excel, we found the critical value of chi-square, which we were using with alpha equals 0.05 and 2 degrees of freedom. And we found that critical value of chi-square was 5.99. So remember that the chi-square statistic is a skewed distribution which starts at 0 and is right skewed. So our chi-square critical value of 5.99 is an alpha value of 0.05, which says reject the null hypothesis if our calculated test statistic is bigger than 5.99. That's how we make our decision. Reject the null hypothesis if our calculated value of chi-square is bigger than 5.99. Now, of course, it isn't. It was 4.07, which we can see on our diagram is between 0 and our critical value. So 4.07 is in the do not reject region. So here we say do not reject because 4.07 is smaller than the critical value of 5.99. 4.07 is in the do not reject region. And this means we have a conclusion that says we have no evidence to suggest that yield and breed are related. We have no evidence that they are dependent. We've no evidence to reject the null hypothesis that yield and breed are not related. So we have no evidence to suggest that the yield and the breed are related or associated. So we could say there is no evidence of a relationship between egg yield and breed of chicken. And that's the end of the example.